start with a new chapter. Okay, basically, took up one section about Euclidean vector spaces, and the material in this section has been covered in the previous chapter of my lectures. So I will ask you to read the material in the textbook, the section 2.1. But I just give you a definition about the Euclidean vector space. So okay, so this is set of one-dimensional column vectors. Okay, so this set is the set of all n-dimensional column vectors. And what we call the n-dimensional Euclidean space. Vector space. So I give the name of Euclidean vector space formula here, and then I also want to give you a remark that okay. To write a column vector, sometimes it occupy lots of vertical spaces, and so so we will write an pentacle x1, x2, up to xn. With parentheses. Instead, because that for such n-tuple, this notation occupies vertical spaces. So sometimes it's more convenient, and they don't interpret such a notation as a row vector, because that a row vector will be written as x1, x2, up to xn with bracket. Okay, so we use bracket to know row vectors, and if we with parentheses, we are referring to such an n-tuple referring to a column vector. So column vector can be written. This is the standard way, but the informal way would be use the n-tuple. Okay, so just for convenience. Okay, so don't be confused about that. Okay, so now second section, line, plane, and hyperplane. Okay, so this section intends to give you some geometrical illustration about linear algebra. Okay, so we start with two-dimensional Euclidean vector space. The line, okay, is determined by two So in the plane, okay, let me write it. In the plane, here, all right. So I say. So in the plane, a line is determined by two distinct points. All right. So say U equal to AB and B equal to CD. Okay. So basically, you actually I said make a remark here. So usually we describe points by column vectors or by n-tuples. Yeah. Right, so a line is determined by two distinct points in the plane. I already said that. By Euclidean geometry. Okay, so when you learn Euclidean geometry, you know a line is determined by two distinct points. And this is the coordinate, right? In the plane. Okay, so let me draw a picture of them. All right, so this is x and y. Okay, and if we have 2 points, so here, so this is U, A, B, and say here, B, C, D. And so the line determined by these 2 points is here, and we call this line L. All right, and a generic point, say here, okay, so this is the generic point on the line L. Okay, great. So so now the vector from point U to point V is V minus U, right? So V minus U is this vector. And this vector is x, the generic point, minus u. So so that x a point, x is on the line L determined by two distinct points U and V, if and only for the arbitrary if and only x minus u. Okay, so this vector x minus u, this difference, is proportional to the vector v minus u. So it's t v minus u. T is in top. So we have a parameter t here. Okay, so this is the economic condition from Euclidean geometry, right? So, or you can, so the point, a generic point, okay, on the line L, which becomes to u plus t v minus u. Okay, so this is the economic condition. So now we can describe the line L, because in Euclidean geometry, a line is a set of points, right? So this line L determined by u and v is a set of points. Okay, the point in the flat, and this quantify such a generic point on the line. Okay, so you see that you have this description. And so that the line describes, right, all the points in the plane such that x is equal to u plus t v minus u. Okay, and which is called a parametric representation of line F. Okay, so now we have parametric representation. So P is a parameter. Okay. All right. So now. Okay, so now we look at the coordinate, okay, of a generic point. All right, so now x equal to xy is on the line. Okay, if only there exists a p in R such that x equal to u1 plus t, v1 minus u1, u2 plus t, v2 minus u2. Okay, so there exists a p in R such as x is equal to u1 plus t, v1 minus u1, and the y is equal to u2 plus t, v2 minus u2. Okay, so a point x is on the line L if only there exists a t. Okay, so if only, so we look at here, so we could write v1 minus u1 and the v2 minus u2, and here we have p equal to x minus u1, y minus u2. Okay, so now these two, right? If you would want to check a point, because the point is a point in the plane, right? And we want to know whether point is on the line or we have to show that there is this p, this point, with this one. So so p becomes too unknown because x, when we are given a point, then x and y are given, right? And of course we know u1, u2, v1, v2 already, so that the only thing is to find a t. Okay, satisfy these two equations. So now we can write down as a linear system. This is a linear system, yeah. Okay, so that this linear system is consistent. Okay, now we have to use our knowledge, linear algebra, right? We learned up to now. So that this is a linear system. Okay, so we have two equations with one unknown t, right? Any questions up to now? Now, so we consider the augmented matrix. So it's V1 minus U1, V2 minus U2, X minus U1, Y minus U2, is implied the depend only the augmented matrix is consistent. If only since U not equal to V, because U, V are distinct points, so at least one of V1 minus U1, V2 minus U2 is non-zero. And we said that V1 minus U1 not equal to 0. So just assume the first one is non-zero, and so it can be derived as a pivot, right? If this is 0, then this one must be non-zero. Then you can swap the two rows. But anyway, you will have a pivot, okay, in the first column. But here, I just say that it says that this one is a pivot already. So, so now I can I will do the replacement to eliminate this entry. So you have okay. So you multiply this at here, then you get V1 minus U1. This is 0, and you have X minus U1 and Y minus U2 minus V2 minus U2 divided by V1 minus U1 and X minus U1. Okay, so now by row operation, that then must be consistent too, because that they have the same solution set, because they are row equivalent to each other, right? So that a point is on the line L, even only if that this augmented matrix is consistent. But this augmented matrix consists even only if what? If only if this entry is 0, right? So if only if Y minus U2 equal to 0. Okay, and I will I will simplify it. U1, U1, Y. Equals to V1 U V1 U2 minus V2 U1. Okay. So that we prove that a point is on the line O if and only if it satisfies this linear equation. So this is the line equation, right? You learned in your junior high school. I just do it backward, right? Because most of the time you study a line from such an equation, right? Linear equation in junior high school. But I pointed this one that basically from Euclidean geometry we have a parametric representation first. Yeah, and then with that, with this argument, we end up with which is a linear equation. Okay, so a line determined by two distinct points U and V is actually is a solution of a linear equation, and then the coefficients here and the constant in the right hand side is determined by the 2 points U and V. So that you have. You might think, wow, this is, I already know this stuff since I was 13 years old, maybe, right? Or 14 years, very young. But the reason why I do this process is because I want to extend the argument to n-dimensional Euclidean space, and for not only lines or geometric objects I will define later on. So this is I believe you know all of the stuff, all the material here, but I want you to review the process. Especially here, I start with a geometrical representation, means geometrical representation up to an algebraic equation here. Okay, so all right. Now I will. Okay, and by the way, any questions? Okay, so you know no question. Now I will do. Now I will go to a line in the three-dimensional Euclidean space. And now we go to a bigger Euclidean space, three-dimensional. Similarly, so given two distinct points. Okay, U equal to U1, U2, U3, V equal to V1, V2, and V3. Okay, so we have two distinct points. There exists one is the only one line. So going through U and V, right? By Euclidean geometry. Again, right? So basically, in n-dimensional space, arbitrary n-dimensional space, not only three-dimensional or two-dimensional, in n-dimensional space, 2 points, 2 distinct points, determine a line. This is exactly what Euclid told you more than 2,000 years ago. Okay. So, but I just confirm myself again in more elementary way. 3-dimensional. You are familiar with 3-dimensional spaces already, right? So that is 3-dimensional. And again, I can just so you might have this is R3. So you have X and Y and then Z here. Okay. So again, you have U here. You have UV here. And then these 2 points determine a line. L. Okay? And we consider a generic point X there. Okay? So basically, a similar way to do it as we have done in the plane. So, so that we have this one. All right, this is U. We have this one. This is X minus U here. All right, so the line will be, just write it down quickly. So this is U plus P again. Okay. So maybe I write here X a point X is on the line L, you can only X minus U equal to P V minus U for some P in R. Okay, so, and then we have a parametric representation. L. All right. So now, all right. So now a point X, Y, Z is on the line L. If and only if, okay, as I just stated here, so that if and only if okay, that exists P R such that V minus U. So okay, and P here equals to X minus U. Okay, and this is just V1 minus U1, V2 minus U2, and V3 minus U3, P, X minus U1, 1 minus U2, Z minus U3. So this is 3 times 1, 1 times 1, and 3 times 1. Okay. So we have a system. Okay. So if and only if the augmented matrix. Alright, V minus U1, V2 minus U2, V3 minus U3, X minus U1, Y minus U2, and Z minus U3 is consistent. Alright, and so that we assume that V1 minus U1 not equal to 0. Okay, so we select this one as pivot, okay, as pivot, and we do the cancellation, right, elimination, so that we have, so to eliminate this one, we have to multiply minus V2, U2, V1, V1, and also minus V3, V3, V1, V1. So we have V1, 0, 0, X minus 1, and Y minus U2 minus V2 minus U2, V1 minus U1, and X minus U1, and Z minus U3 minus V3 minus U3, V1 minus U1, and X minus U1. Alright, so this is consistent. Okay, so if and only that these two entries must be 0. So we have, so if and only if that Y minus U2 minus V2 minus U2, V1 minus U1, X minus U1 equal to 0, and Z minus U3 minus V3 minus U3 divided by V1 minus U1, X minus U1 equal to 0. So we have two linear equations. So in the 3-dimensional space, we need two linear equations to determine a line. Okay, so this is probably learned, I think, probably in high school already. Right? So we have two linear equations. Oh, one more thing. A plane R3. Okay. So consider 3 non-collinear points. So we have U equal to U1, U2, U3, V equal to V1, V2, V3, W equal to W1, W2, and W3. Alright, so we can say it's non-collinear. It's very important. Okay, so by Euclidean geometry, these 3 points determine a unique plane in R3. Okay? So Euclid told us that it's one. So 3 non-collinear points. Okay, so now we have to transform verbal description, non-collinearity, by using terminology or concept we have learned in linear algebra. Okay. So let's see how to describe it. Well, now I will describe the opposite, the negative of this situation. So now, 3 points. U, V, W R3 are collinear if and only if U minus V minus U is equal to T times W minus U. What? Well, when you we say that 3 points are collinear, so you see it's a geometrical situation. So we have so they are collinear means that they are on the same line. Say here L. So we have a point U. We have a point V. And also we have a point W. So now V2, so that this vector from U to V is this one. So this is V minus U. And this vector is W minus U. When these 3 points are on the same line, so the difference, the red vector is parallel to the green vector, so that they are proportional to each other. Okay? This is from the geometrical situation. So you have this one. So the 3 points are collinear if and only if we have this. Okay? For some T. Now, and P is not equal to 0. Why? Because, or that's fine. Just there. And so, V minus U minus P W minus U is equal to 0. And we have 1 here, right? So this if and only if the set of 3 minus u and w minus u. So we have two vector. So this set of vector is linearly dependent set. Okay, so we interpret it here. So they are linearly dependent. Okay? So this is economic condition. Alright, so now we can say that 3 points U, V, W are non-collinear. If and only V minus U, minus U is linearly independent. Okay, so now because by Euclidean geometry, a plane is determined by 3 non-collinear points. And we know 3 points are non-collinear if only if these two different vectors is nearly independent. Okay, so the linear independence is important to construct a plane in the 3-dimensional space. Okay? So this gives you the reason why we have to study linear independency or linear dependency on vectors. Yeah, because it is directly related to some geometric concept. Okay. So now the plane. So a point. Now a point X is in the plane H. Okay, in the plane H determined by 3 non-collinear points U, V, and W. We can only X minus W is equal to S minus W plus P minus W. Okay, so let me draw it. X, Y, Z. Now we have 3 points. We have this is W. We have U. We have V. And you can see these 3 points are not collinear, so they determine, all right? And So the plane will be the plane determined by this triangle, right? So the plane will sit on this triangle. Okay, the plane. All right, and so when we look at say a generic point on the plane, a generic point in the plane H, then this vector, which is x minus w, and this vector, which is u minus w, and this vector u minus w. Okay, because they are on the same plane, so that this vector is obtained, can be obtained by using the parallelogram. So see, okay, so I will do it geometrically. Okay. Probably I think it's better because it's a little bit harder to write it. So maybe I just say here. This is x. The point x. Okay. So so the way is that we use parallelogram here, and so okay. So we have one. Okay, so x, and so the parts here, which is t minus w, and for this part is x u minus w. So the rate vector is the sum of this vector and this vector, right? So now I can write this way. For some st r. I'm sorry, I overlaid the graph with my text. Is that okay for you? Do I need to redraw the graph in other place? Okay. So So this vector is proportional to the yellow one, right? And this vector is proportional to the green one. So the proportionality is this one is P. And you sum together because of the parallelogram construction, vector addition, right? By using parallelogram. So we have this one. Okay, so the hyperplane, and so this is saying that x is equal to w plus x u minus w plus p v minus w, and thus the h can be described by here x is equal to w plus x v minus w and the t v minus w. So a parametric representation of h. Okay, so it's a parametric representation. So now, a point x is in H, if and only if, as we write down here, x minus v minus w is equal to su minus w plus t v minus w. Okay, and now we can, for some xt r. So now we can write this vector equation as metric equation. So we have u minus w and v minus w. So we have two columns and s and t here equal to x minus w. So this one is 3 times 2. This is 2 times 1. And this one is 3 times 1. So that would be u1 minus w1, u3 minus w2, u3 minus w3, and v1 minus w1, v2 minus w2, v3 minus w3, st, x minus w1, y minus w2, z minus w3. So you have a linear system. Okay, so you have a linear system. Okay. So the linear system is consistent. Means that you have x and y, you have solution. Okay, so a point x, y, z is in H if and only if this linear system is consistent, and if only if the augmented matrix is consistent. Alright. Now, suppose that because that U and W they are distinct, right? And so that at least one of these is non-zero. But the most important thing is that these two columns are linearly independent, as we know, because they are collinear, right? Here. Because they are collinear. So that the difference is, so they are linearly independent. So these two columns form a linearly independent set. So the consequence is that we have pivot position. Okay, from chapter 1, so we have two pivots. Each column has a pivot. Okay, so this is implies that only if that each column has a pivot. Okay. So each column has pivots. So without loss of generality, we say this is a pivot and this is a pivot. Okay. All right, so we can, so the augmented matrix, so we can have W1 minus W1 a pivot. And the root of 0, 0 cancel them. And the V1 minus W1. This is X minus W1. And also, we will have something. So we end up with so that so we finally will have 1 and 1 here and 0 0 and here because of the cancellation so cancel okay. So we will have something like alpha 1 x minus w1 plus alpha 2 y minus w2. And we have beta 1 x 1 plus beta 2. And the final thing here is we have gamma 1 x minus w1 plus gamma 2 y minus w2 plus gamma 3 z minus w3. Okay. By row operations. So we can do obtain by Gauss-Jordan elimination. We can obtain a row-reduced echelon form for the coefficient matrix here. Okay. And the reason why I put here is because that for these two entries, because this one will eliminate this entry, and then this entry will eliminate this. The paper will eliminate this entry. No matter why, the here will involve linear combination of this one and this one, these two components. So we have, in general, we have alpha 1 times this and alpha 2 times this. So you have to determine alpha and alpha 2, because alpha and alpha 2 determine on the entries here. And for this is the same. But for the third row here, because you may use the replacement from here and here to there. So in general, you have a linear combination like this. Okay. And so that this one should be consistent. This is consistent. All right. So finally, gamma 1 plus gamma 2 for some gamma 1, gamma 2, gamma 3. So a plane in the three-dimensional Euclidean space can be described by one linear equation. Just only one linear equation here. Okay. So the important thing is that we end up with, because these two columns are linearly independent. Okay, so we have pivots in each column, so that the reduced echelon form must be here, like this one, because we have two pivots. And the reduced echelon form is unique for the coefficient matrix to find it. And so the last column should be this one. Okay? Because we are doing the wrong operation. Alright, so I have to stop here and give you a short break, and we will start the